So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to be talking about the Gauss hypergeometric function. Okay, before that, let me tell you, and actually, let me apologize in front of you all that it's been a long day that I recorded here, like just teaching on my blackboard. Actually, you know what? I was having trouble with my blackboard, so I need to fix that down. And now I'm here after fixing all the things, and now let's just begin our journey. So basically, we are going to be talking about the Gauss hypergeometric function. Although I have never talked about this in my previous videos, and this is going to be the first video of this. Okay. So this is the hypergeometric function. Let me just explain it to you firstly. So this is the representation of the hypergeometric function, right? It's 2 of f of 1. I'm not sure like how to just how to pronounce it, but just adjust it, guys, because I just want you to just visualize it. Don't just come up to my words. Okay, so it's and I'll tell you why it's 2 and why it's 1 over there. That's a pretty amazing fact, and I'm sure that after listening that thing, you're gonna be like, wow, this is amazing and this is literally cool. Okay, so basically it's 2 and f of sub 1, you can say, of a comma b such that c such that z equals the sum as n goes from 0 to infinity of, well, let me just explain it to you actually. First of all, the tools of us to just use here is, the first one is generalized binomial theorem, and this is the infinite sum actually. It's 1 minus x to the minus a, and this is being represented with an infinite series, that is the sum as n goes from 0 to infinity of like the Pochamer series, or you can say the Pochamer sum, right? And it's a of n, you can say, over n factorial, and it's x to the n. And what's the Pochamer symbol? Although I have talked about the Pochamer symbol once in my old videos, but I haven't made any dedicated video over this, so it's quite difficult to find that video in which I just explained it to you. So that's why let me just explain it to here as well. So it's just a representation, you can say. It's gamma of x plus n over gamma of x. That's it. So it's the Pochamer symbol actually, right? And it's the representation, and it's the meaning of the Pochamer symbol. Gamma of x plus n over gamma of x, right? So it's a sub n and times b sub n and over c sub n. It's the Pochamer symbols over there, and it's z to the n over n factorial. So this is basically the you can say the hypergeometric function, the fundamental, or you can say the most basic, or you can say the very first entrance of this world, that this is the function actually, the hypergeometric function. And now what I have written down below right here, what's that? So it's another representation of the hypergeometric function. And guess what? Who did like expressed it? Obviously, most probably it's Euler. So yeah, it's Euler as well here. So it's Euler's representation, or you can say Euler's integral representation. And yeah, that's pretty amazing. And I would request you guys, don't get confused with this generalized binomial theorem. And I'm looking for the proof of that as well, but not today, and I'm just going to take a dedicated video about that. So for now, let's just talk about this integral. In order to prove this down equals to this, the basic, or you can say the fundamental hypergeometric function. Okay, so let's just talk about the proof. Okay, let's just go back to that. So let's consider this integral as I. So here we are having I as gamma of c over gamma of b times gamma of it's c minus p, right? And times integral from 0 to 1, and it's t to the b minus 1 and it's times 1 minus t to the b minus c minus 1. I hope you guys can see all the stuffs properly. Well, I think I should just check this out once because I don't want any sort of trouble. Okay, and I'm just copying that down, so yeah, and it's 1 minus t z to the minus a dt. Okay, so let's consider that as I. And now we're going to be using this very, you can say, tool here. And okay, so let's use that generalized binomial theorem. So from our tool, we have 1 minus x to the minus a equals the sum as n goes from 0 to infinity of a sub n over n factorial, and it's, wait a second, x to the n, right? Okay, so for our case we have to plug x equals tz. So this is what we have to plug over here, and I think, yeah, I need to tell you this, that the absolute value of x should be less than 1, right? Yeah, and here you have to consider t in the range of 0 and 1, and again like z is less than 1 actually, absolute value, right? Okay, so when we plug x equals tz, it's 1 minus tz to the minus a equals the sum as n goes from 0 to infinity of a sub n over n factorial, and it's tz to the n, right? Okay, and basically, yeah, a times b whole to the n is a to the n times b to the n. So here we can say it's t to the n times z to the n as well. So let me just not take another step to that. So it's t to the n and times z to the n. So let's just consider this equation here. Okay, and now what we're gonna do here is we have to just plug this back right over here. Oh wait a second. Okay, so right over here actually. So this is what where we have to plug this infinite sum, and let's just see what we're gonna have. And believe me, we're gonna have a very interesting thing, because you are here to see interesting things, don't you? Okay, I'm having a lot of fun, dude. So let's just okay, so now just plugging back this representation of this function over there inside that integrand, right? So I equals is gonna be gamma of c over gamma of b times gamma of c minus b, and times integral from 0 to 1 of t to the b minus 1 and 1 minus t to the b minus c minus 1, and times the infinite sum as n goes from n goes from 0 to infinity of a sub n over n factorial, and it's t to the n and z to the n dt, right? And that's it sounds amazing, isn't it? And now what we have to do here is, due to linearity, we can say that the signs of this integral and the sum are gonna be interchanged to each other, and we have to just plug some sort of things out of the integral, that this z to the n, and like we have to just keep this inside the integrand, because obviously it's depending on t, and despite of that we can just plug all the things out. So let's just do this. Okay, so we have I equals gamma of c over gamma of b times gamma of c minus b, right? And we are having the infinite sum, right? We can say that we have done a lot of things like this, so it's not the first thing, right? It's not. Okay, and it's a sub n over n factorial, and it's z to the n as well. And now let's just talk about the integral part. So integral from 0 to 1, and it's, well, you know what, we can consider just multiplying this t to the b minus 1 times t to the n, don't you? But can't we actually? it's t to the b plus n minus 1, right? Just using the basic exponential rules. So it's integral from 0 to 1, and it's t to the b plus n minus 1, and we are having 1 minus t to the b minus c minus 1 dt. And now we are gonna be introducing some sort of a thing which we are familiar of, you can say, for a very long period of time. And if you are having still any sort of doubt of that, I have made a lot of videos. You can consider watching those things, and that is beta function. So let's just introduce that. Welcoming beta function here, guys. So, and why welcoming actually? Because we can use our brain to just recognize here that we are having an integral, and that is quite, not quite, but exactly related to the beta function. So basically, let me just explain a little bit about the beta function. So beta function, right? Okay, so it's beta of x comma y, and it's the integral representation of integral from 0 to 1 of t to the x minus 1, 1 minus t to the y minus 1 dt, right? So here we are having the integral. So what if we plug x equals b plus n and y equals b minus c? It's the same stuff, and guess what? This integral right over here is beta of b plus n comma b minus c. Don't be like, yeah, obviously it is. When you plug x equals b plus n and y equals b minus c, so beta of b plus n comma b minus c is integral from 0 to 1 of t to the b plus n minus 1 times 1 minus t to the b minus c minus 1 dt. So, and this is the integral that we have to evaluate. So basically it's this thing, and already I have represented it to that. And we are not gonna be writing this in terms of that only, because we know that there is another representation of the beta function. It's gamma of x times gamma of y over gamma of x plus y. So if we plug x equals b plus n, so this integral is gonna be gamma of b plus n and gamma of b minus c over, and when we just add these things up, so it's b plus n. Oh, wait a second. Hey, wait. I think I am wrong a little bit. I need to check this out. Oh, I'm so sorry, guys. It's oh, wait a second. It's c minus b. It's not b minus c. I'm so sorry. It's c minus b. I'm so sorry, guys. I obviously I did messed up there. I'm so sorry. Please correct that down. C minus b, right? And it's c minus b. I'm so sorry. I'm extremely sorry about that. I must have done something wrong over there. Now it's perfectly fine. Okay. So basically, when we add these two things up, so b plus n plus c minus b. So b minus b cancels out, and we would be having gamma of c plus n. Don't be. So that's what we are having on the place of this integral. So now our next step is represent this integral in terms of that gamma function. So let's just do that right away. And yeah, that sounds good, but I was not expecting that I was going wrong, but it's all right. Okay, so basically your I is gamma of c over gamma of b times gamma of c minus b times the sum as n goes from 0 to infinity of a sub n over n factorial, and it's z to the n, and this is gamma of b plus n times gamma of c minus b over gamma of c plus n. And guess what? We are having gamma of c minus b outside in the denominator, and we are having its inside on the numerator, so it doesn't mean, because it's not obviously depending on n. So we just got rid of that thing, and now let's just talk about the rest of the things that we're having. Okay, so now we are going to be playing, or maybe we're going to be introducing two Pochamer symbols. Are we going to do that? Now I'm just going to insert these two things inside this sum, because we can do that. It will not bother us. We are having a of n, a sub n you can say, and you can say gamma of b plus n over gamma of b, writing this over here, and we can say that it's 1 over gamma of c plus n over gamma of c, because eventually that's going to be in the numerator, and that's what we had there. And finally we have this rest of the things, that is z to the n over n factorial. And why I have done that? Because when you look at the you can say the generating function of the Pochamer symbol, it's gamma of x plus n over gamma of x. So for our case, we are having this sum as n goes from 0 to infinity of a sub n, and this is going to be your b sub n, and we are having the denominator, we have c sub n, and we are having z to the m over n factorial, and this is what we like, this is the you can say the generating function of the hypergeometric function. And that's why we just did those things. We just did all the things actually. We just began with the hypergeometric function, and then we just understood the Euler's integral representation of the hypergeometric function, and then we just proved the Euler's integral representation of the hypergeometric function equal to the actual hypergeometric function. So that was the motive of this video, but we're not done yet. As I just you can say, do you remind me that we had started something sort of here, that this was the representation of the hypergeometric function, a, b, c, and it's z, right? So why it's 2 and 1? Guess what? Because this 2 is representing these two parameters in the numerator, and this one is representing the denominator, the parameters. So basically, if we talk about this thing, that is 3 or 2, so that's gonna be representing that this 2 is 2 parameters in the denominator, right? This Pochamer symbol, and 3 is in the numerator actually. So we would be having 3 Pochamer symbols in the numerator, although it's not gonna be like that. This is not gonna be the you can say the argument, because it's not enough, right? And we would be like having some sort of, you can say it's we need to have we are having 4 here, and we have 3, right? So 5. So we will be having 6 things, you can say 6 things, a, b, c, d, and then z. So for that case it's this. So a, b, c, d, e, and then z, right? So that's gonna be representing the this hypergeometric function, right? So that's why this is, that's why it is written like that. So this is really mind-blowing, and yeah, we did that, guys. And actually now my focus is now to prove this thing, because we did use of that, but we haven't proved it yet. So for that case, please make sure to like, subscribe, and share, and just love it. Okay, first of all, you have to wait for that. I have to work over that obviously. And the second thing is, if you have any kind of doubt so far, you are free to ask me in the comment section. I'll be there to reply over your questions. And please guys, like this, and because if you liked this video, please, it's your work to just support me, and I think it's enough. And again, guys, just learn mathematics, have fun, live your each moment, and just love your life. Whatever it is, it's not sure how long will it be. So for that case, love your life, enjoy, and learn mathematics if you're following me. Thank you so much for watching this video, guys. Goodbye, take care, love you, and just have fun and get back to the proof, to see the proof of that thing. Okay, I think now it's the good way to just show that. Okay, goodbye, guys, love you, take care.